Welcome to a new episode on my exercise series Introduction to Physics. And welcome to the Millennium Tower that you can see here. I'm right now in Magdeburg, and this special tower here in front of me has been built 20 years ago, and it is the highest wooden building in the world. And inside there is a technical museum where you can find lots of hand-on experiments. So let's get in and welcome inside. Yes, there are many different experiments, but today I want to show you this one, this rope and pulley system that you can actually try out yourself and try out what's it for, how does it work, and what actually are forces and how strong do I have to pull to lift masses that are way too heavy to lift normally by just, pulling them up. But using such a rope and pulley system, even heavy masses can be pulled up quite easily. And this is what we actually want to calculate today. So welcome to today's exercise. Here we have today's task. The masses M1 equals 1 kilogram and M2 equals 2 kilogram are connected by a rope and pulley system. Masses and friction of the system are neglected. A. What force is needed to hold M1 on the pad? What is the force in the rope when M1 is held on the pad? And C. What is the force in the rope when M1 is released? As always, we start with having a look at what variables and values are given and what are we searching for. What are the given variables? First of all, we have given the mass M1 being 1 kilogram and M2 being 2 kilograms. Both are given in their basic units, so we do not have to recalculate them. What are we searching for? Firstly, we are searching for the force that is needed to hold M1 down. Secondly, we are searching for the force in the rope when we hold M1 down. And thirdly, we are searching for the force in the rope when M1 is released and can move free. So let's make a short scheme. As shown here, we have this rope that connects our two masses, and in between we have our pulley system, a very simple one, nothing much to look at. But we know that M1 is half the mass of M2. So basically, when we look at it, we know that M2 would just move downwards and therewith moving M1 upwards. But in the first task, we want to find out how much force do we need to hold M1 down. So basically, we do have two forces, both pointing downwards. One is F1 that is associated with the mass M1 and the other one is F2 associated with M2. And we know those two forces are nothing special. They are just gravitational force and they are a product of the respective mass and the gravitational constant g. And we know that g, when we want to use it for calculation, is 9.81 meters per second squared. Even though when we actually measure it all over the world, we will get slightly different values depending on the actual location. So, what do we have to take into account? Well, the two masses are connected by the rope. Hence, if we follow the rope starting on the right-hand side at mass M2, the gravitational force points downwards. So, when we go along the rope, we find that, of course, the mass M1 is pulled upwards with exactly this force, while at the same time its gravitational force, F1, tries to pull it down, but it's too light. So we need an additional force to hold M1 down. And this is exactly what we are supposed to calculate in the first step, the additional force to hold the mass down. And we've just seen in the scheme how this would work. So we need the force F1 plus an additional force, let's call it F hold, and the sum of those are going to be equal to F2. And we already have seen also what F1 and F2 are. They are exactly the gravitational forces. And since we want to calculate F hold, we can just rewrite our equation such that F hold equals F2 minus F1. And this is equal m2 times g minus m1 times g. So it's nothing special that can be seen here, and we can just take our values for the gravitational constant and the masses, all given in their basic units, and put it in a calculator, and what we get is that the force to hold the mass m1 down equals 9.81 Newton. Now, of course, to be precise, it has to be minimum of 9.81 Newton. If it's larger, of course, we would also hold m1 down. But we need a minimum force that's exactly given here. So what was the second question? B was the force in the rope that we are looking for to hold m1 down. So let's go back to the scheme for a moment that is shown here again, and we've seen that when the force of gravitation on m2 is pointing downwards, we can go around and we see that on the left hand side it's pointing upwards. And now we are looking for the force in the rope. But the force in the rope doesn't change whether I'm just holding m1 down or holding the rope above m1 at exactly the same point, or if I just go along the rope to the right hand side of my scheme and just grab it right here where it's shown. So I can basically neglect all the things on the left hand side of my scheme and just grab my rope on the right hand side right above m2. And this makes it actually pretty simple to calculate the rope force, because F rope equals exactly F2, and F2 was the gravitational force of mass 2. So we can just substitute F2 by m2 times g, and since those values are given, it's really easy in this case to calculate the force that we are looking for, and what we get is that the rope force equals 19.62 newtons. Are we done yet? No, not exactly. We are still looking for the force in the rope if the system moves freely. And this is actually a bit more complicated to calculate, but let's make it simple. Let's put down the diagrams of the forces separately. So here on the left hand side we can see our mass m1, and it has a certain gravitational force F1. On the other hand, there is a rope force F rope 1 that's pointing exactly in the opposite direction compared to F1. And on the right hand side we do have the same for mass m2. It has a gravitational force F2 and the rope force F rope 2. And you can see that the rope force equals the gravitational force, but you can also see I put it down here separately, whereas in our task, of course, it's a pulley system, so they are connected. They are not independent. What can we do? Of course, we can put it together. We know that the rope force, if the system moves freely, let's call it F free, is exactly the same as the rope force F rope 1, and it has to be the same as F rope 2. This just means that the rope is not, hanging limp or going all over the place. It's very steady and moving at a steady pace, which means there is another factor that we have to take into account, and this is the accelerations. What about them? Of course, they are not independent again. When we think about it, we know that mass m1 is moving upwards. So let's say a1 is positive. Then a2 has to have the same value, but it has to have a negative sign because mass m2 moves downwards. So let's say the total acceleration a will have a negative sign, will point downwards. Does this help us? Well, when we go back to the scheme that shows our forces as independent, we can actually write down the necessary equations. So on one hand, we know that the force, if it actually moves free, F free, minus the gravitational force, would be the rope force in case of mass 1. So F rope 1. And we can substitute it. On one hand, F1 we've seen before is just the product of mass 1 and gravitational constant. And on the other hand, we know that such a force is always the product of mass and acceleration. And if we do not know the acceleration, we give it a general name. And we've already done it. We've said that mass m1 accelerates with an acceleration of a1. And since we know that a1 equals minus a, as we've seen it on the previous slide, we can write this down as f3 minus m1g equals minus m1a. And we can do the same for the forces regarding m2, and there is no mystery that in this case we've seen before that a2 points in the same direction as the general acceleration a, so f3 minus m2 times g equals m2 times a. So they look similar enough, but you can see especially on the right hand side, on one hand we have the minus, on the other hand it's not there at all. So what do we want? No, we do not want the acceleration at all. So a is a parameter, a variable that we do not need and we do not want. We have two equations and two unknowns. So let's delete a. Let's take, for example, the first equation and divide it by m1. And we can put it into the second equation. And what we get is shown exactly here. The only unknown parameter right here is actually the force F3, the force in the rope of the system moves freely, that we are looking for. So let's take this equation and just put it in a different form. Of course, first of all, we can multiply the whole equation by minus m1. And in the second step, we put all terms where f3 is a part of on the right hand side, all other terms on the left hand side. And then we can actually calculate the force F3 that we are looking for as 2 times m1, m2 multiplied by g, and all of it divided by the sum of m1 and m2. And since all our given values are in their basic units, we can just put them in the calculator and calculate that F3 equals 13.08 Newton. And with this, we've actually solved a very simple problem that you may stumble upon from time to time. And such rope and pulley systems are very nice to look at, and they are actually very nice to play around with, and they have been around not, for a couple of years, but already for centuries. Actually, they have been around for 4,000 years. There are historic drawings from ancient Egypt or ancient Mesopotamia that show such pulley systems where forces are redirected in a different direction or actually used to lift heavy weights. And with this, I would like to thank you for your attention, and I hope this was helpful, and I hope to see you soon for the next video. Bye!